Okay, so here's our example of the type of problem that we might run into for the first learning objective in our electric potential and capacitance section. So we're asked to find the electric potential at 2 points on this triangle arrangement. The charges in question are forming an electric dipole, which means they have an equal magnitude but opposite sign and are just separated by a distance. In this case, the distance between the two charges is 10 centimeters. The two charges are at the base of an isosceles triangle, where the two equal sides have a length of 13 centimeters. In the first part of this question, we're asked to find the potential at point A, which is a point along the line joining the two charges, but not at the very center. So to try to write this in a more general way first, I'm going to say that the potential at point A is going to be equal to the potential at A due to Q1 plus the potential at A due to Q2, and we add those two together. I'm going to call this distance RA1 to represent the distance to point A from charge 1, and then we have KQ2, and I'm going to call this distance RA2 to represent that it's the distance between charge 2 and point A. So if we then substitute in our values for this, remember a nanocoulomb is 10 to the minus 9, this distance is 0.06, and then we have and we have 9 times 10 to the 9, and then that's minus 12 nanocoulombs. And this distance is 0.04. I thought it was really helpful if I just factored out some common terms. And this is going to be how I'm going to calculate the potential at point A. This just makes it a little easier to do my calculations. And so this is going to be, if I multiply the 9 times 10 to the 9th times the magnitude of the charges, I get 108. And then my inverse of my distances gives me 16.67 minus 25. And this is actually going to give me a negative potential. If I think about that, that should make sense because the potential is going to be dominated by the negative charge because it's closer to that. And so the potential at point A is minus 900 volts. If I do the potential at point C, which is at the apex of my isosceles triangle, you might realize that my distance in this case is going to be the same. And so the charges are actually going to cause these two terms to cancel out because I'm going to get 9 times 10 to the 9th if I have the magnitude of the charge and do what I did last time. I have 1 over 0.13 minus 1 over 0.13. And so I'm going to find that the potential at point C is 0. And that makes sense because these two charges of equal magnitude but opposite sign, and because I'm equidistant from each of them, the one will have a positive potential, one will have a negative, they'll be exactly the same magnitude, and so they cancel out. Now finally, in part C, we're going to ask to find what is the potential energy associated if we put a 4 nanocoulomb charge at point A. So here we're using the relationship between potential energy and potential. And so we know that the potential at point A represents minus 900 volts. If we put a charge at that location, then we'll know what the potential energy associated with that is. So we get 4 times 10 to the minus 9 times the minus 900 volts. And this will give us minus 3.6 times 10 to the minus 6 joules, or I could write it as minus 3.6 microjoules. And so that's just a simple example of the type of problem you might run into.